Welcome to iRobot. I'm Kishore Kumar Vajja. In this video, we are going to learn how to build a convolutional autoencoder using Keras. Convolutional autoencoders are an autoencoders. It can encode an image into a code, that is, a representation vector or latent space. From this code, it can reconstruct the original image as and when required. Convolutional autoencoders using convolution operator for filtering input images in order to extract some part of its content. Autoencoders used for data compression. Data compression is very essential in computer vision, computer networks, computer architecture, data science, and many other fields. Autoencoders are used to reduce the size of our inputs into a smaller representation. If anyone needs the original data, they can reconstruct it from the compressed data. Let's see, what is an autoencoder? Autoencoder is an unsupervised neural network. It learns to encode an input in a set of simple representation vectors, that is code, and then it tries to reconstruct the input from these representation vectors with minimum possible error. This means that we want the output to be as close to the input as possible. It can also modify the geometry or the reflectance of the image. Basically, the autoencoder consists of an encoder, a latent space, that is code, and a decoder. An encoder that compresses the input image via input layer into a latent space representation, that is code, in a reduced dimension. The compressed image is the distorted version of the original image. The code is the compressed input and it gives a representation vector like -2.5, 0.6. Decoder decodes this vector and reconstructed original image. The decoded image is a lossy reconstruction of the original image and it is reconstructed from the latent space representation. The layer between the encoder and decoder, that is the code, is also known as bottleneck. The representation vector is a compression of the original image into a lower dimensional, that is latent space. The idea is that by choosing any point in the latent space, we should be able to generate novel images by passing this point through the decoder, since the decoder has learned how to convert points in the latent space into viable images. Let's see the applications of autoencoders. Image colorization. Autoencoders are used for converting any black and white picture into a colored image. Depending on what is in the picture, it is possible to tell what the color should be. Generally, in an image, sky is in white, grass is in green, and clouds are white. Second application, feature variation. Autoencoders extracts only the required features of an image and generates the output by removing any noise or unnecessary interruption. Third application is dimensionality reduction. Dimensionality reduction was one of the first applications of deep learning, and it is one of the early motivations to study autoencoders. In a nutshell, the objective is to find a proper projection method that maps data from high feature space to low feature space. The reconstructed image is the same as our input but with reduced dimensions. It helps in providing the similar image with a reduced pixel value. Representing data in a lower dimensional space can improve performance on different tasks such as classification indeed. Many forms of dimensional reduction place semantically related examples near each other, aiding generalization. Next application is denoising image. The input seen by the autoencoder is not the raw input, but a stochastically corrupted version. A denoising autoencoder is thus trained to reconstruct the original input from the noisy version. Next application is watermark removal. It is also used for removing watermarks from images or to remove any object while filming a video or a movie. The next application is machine translation of human languages. The language text are encoded into the learning procedure, while in the decoder side, the target languages will be generated. Recent years also see the application of language-specific autoencoders to incorporate the linguistic features into the learning procedure, such as Chinese decomposition features. Autoencoders are used in popularity prediction. Recently, stacked autoencoders framework have shown promising results in predicting popularity of social media posts, which is helpful for online advertisement strategies. Autoencoders are used in information retrieval, anomaly detection, drug discovery, population synthesis, and many others. This is the complete block diagram of convolutional autoencoder, which we are going to build using Keras. This convolutional autoencoder consists of an encoder, a code that is latent space, and a decoder. The network is trained to find weights for the encoder and decoder that minimize the loss between original input and the reconstruction of the input after it has passed through the encoder and the decoder. In the encoder, we have used four convolutional layers. These layers will take images from the preceding layers and convolve with them the filters. After every convoluted layer, we have used a leaky ReLU activation function for updating the weights through back propagation. Next, we have used a flatten layer for converting the data into a one-dimensional array for inputting it to the next layer to create a single long feature vector. And its output is our code, that is latent space or representation vector. From this input layer, we will pass the images to this encoder. The encoder takes an input image, for example, say 28 by 28 by 1 size of image. It passes through a series of convolutional filters and encodes it into the code, that is 2D latent space. And you can also call it as representation vector. For example, its output may be like this, minus 2.5 comma 0.6. For every image, we will get this type of representations. Note, for more information about input layer, convolution layer, leak ReLU activation function, flatten layer, and dense layer, please visit my previous tutorial if required. I have given the link in the description. Please see. The decoder takes a point from this latent space and passes through the dense layer and deconvolution layers, that is convolution transpose layer. Its output is a decoded image of our original image. Convolution transpose layer. Standard convolutional layers allow us to hollow the size of an input tensor in both height and width. By setting strides equal to 2, the convolutional transpose layer uses the same principle as a standard convolutional layer, that is, passing a filter across the image, but is different in that setting strides equal to 2 doubles the size of the input tensor in both height and width. In a convolutional transpose layer, the strides parameter determines the internal zero padding between pixels in the image. Original image is encoded into low-dimensional image by an encoder. The convolution transpose layer works on this low-dimensional image with filters. A 3 by 3 by 1 filter, that is gray, is being passed across a 3 by 3 by 1 image with strides equal to 2. It produces a 6 by 6 by 1 output feature map. In Keras, A Canvu 2D transpose layer allows us to perform convolutional transpose operations on tensors. By stacking these layers, we can gradually expand the size of each layer using strides of 2 until we get back to the original image dimension of 28 by 28 by 3. Let us now build convolution autoencoder in Keras. First, we need to import required packages. Using this code, we will import MNIST database of handwritten digits. It has 60,000 grayscale images of size 28 by 28 of the 10 digits along with a test set of 10,000 images. Loading the dataset. Using Keras, MNIST data is loaded to the network. It returns two tuples, x underscore train and x underscore test, or the unsigned integer of 8-bit array of grayscale images data with shape of 60,000, 28 by 28 for training images and 10,000 of 28 by 28 testing set images. Y underscore train and y underscore test. It is unsigned integer of 8-bit array of digit labels, that is integers in range 0 to 9 with shape. We can confirm this by plotting the first sample in matplotlib using this code. Similarly, second sample. Here we need training data and testing data for encoding and decoding. So we will scale the training and testing data only using these lines of code. Reshaping the dataset. When using the TensorFlow backend, you must explicitly declare a dimension for the depth of the input image. For example, a full color image with all 3 RGB channels will have a depth of 3. Our MNIST images only have a depth of 1 because they are gray color images. But we must explicitly declare that. In other words, we want to transform our training dataset from having shape 60,000, 28, 28 to 60,000, 28, 28, 1 and test dataset from having shape 10,000, 28, 28 to 10,000, 28, 28, 1. Now we need some parameters for this programming. So we need to declare now. This is our image's shape. This is number of filters for 4 convolution layers. And this is number of 3 by 3 kernels for 4 convolutional layers. This is for different strides for 4 convolution layers. This is number of filters for 4 deconvolution layers. This is number of kernels for 4 deconvolutional layers. This is for different strides for 4 deconvolution layers. And this is total number of dimensions for our latent space. Now we will build encoder. In an autoencoder, the encoder's job is to take the input image and map it to a point in the latent space. To build encoder, we first create an input layer for passing the image using this line of code. Here we have passed shape of image with a name to the input layer and stores this input as our encoder's input. Here we are going to design our encoder with 4 convolutional layers using these lines of code. We will get a value, it is 4. Using this code, we have assigned our input images to a variable called x for later use. Using this for loop, 4 convolutional layers will design with different strides and filters. Using this line of code, the input image is passing through these 4 layers and each layer will capture high-level features. We have used a stride of 2 on some of the layers to reduce the size of the output. After every convolution layer, we have used a DT-ReLU activation function for updating the weights through backpropagation. This line of code gives the values of shape before flattening. This will be used in the decoder section. This line of code flattens the last convolutional layer. Using this code, the flattened layer connected to a dense layer of size 2, which represents our two-dimensional latent space. Using this line of code, we build the model for encoder using Keras model. Our model that takes an input image and encodes it into the 2D latent space. Let's see the summary of our encoder. From this summary, input image dimension is 28 by 28 by 1. It means it is a grayscale image of size 28 by 28. It is passed through input layer. Next, the image is passed through first convolutional layer, which has 32 filters, each having size of 3 by 3 kernels with stride equal to 1. This convolutional layer will capture high-level features from this image. Next, leaky relu activation function applied to this image for updating the weights through backpropagation. Next, this image is passed through the second convolutional layer of 64 filters of kernel 3 by 3 size with strides equal to 2. Here also, same thing done as in the first convolutional layer, that is capturing high-level features. But its output feature map will be hollowed due to the strides equal to 2. So the output shape is 14 by 14 by 64. Next, leaky relu activation function updates its weights through backpropagation. In the similar way, the image is hollowed in the third convolutional layer due to strides equal to 2 pyramid. After updating its weights by leaky relu activation function, the image is passed through fourth convolutional layer and updating its weights by leaky relu function. This image is passed through flatten layer for flattening the image to connect to the next dense layer of size 2, which represents our two-dimensional latent space. Our encoder takes an input image and encodes it into the 2D latent space. Here, trainable parameters are 98,946 and the non-trainable parameters are nil. Note, you can change the number of convolutional layers in the encoder simply by adding elements to the list that define the model architecture. I strongly recommend experimenting with the parameters that define the models to understand how the architecture affects the number of weights in each layer, performance, and model runtime. The decoder. The decoder is a mirror image of the encoder, except instead of convolutional layers, we have used convolutional transpose layers. Using this code, given input to the decoder is the point received from the latent space, that is code. Using this code, we have connected the input to a dense layer. We have already obtained shape underscore before underscore flattening value from encoders section. Using this code, reshaped this vector into a tensor that can be fed as input into the first convolutional transpose layer. It determines number of convolutional transpose layers, that is 4 layers. Using this for loop, we have designed 4 convolutional transpose layers with different strides. This code stacking these 4 convolutional transpose layers on top of each other. Using this code, we have used 3 leaky relu activations after every convolutional transpose layer and 1 sigmoid activation after the last convolutional transpose layer. The sigmoid activation function is useful if you wish the output from the layer to be scaled between 0 and 1. This is the required output. Using this code, the Keras model designed for the decoder. Here, input of decoder, which takes a point in the latent space and decodes it into the original image domain. Now the summary of decoder is decoder.summary function. From this summary, Input to the decoder is a two-dimensional representation vector, that is code. It is from the latent space. These vector values are passed through the dense layer. Next, it is reshaped. This reshaped representation is passed to the first convolution transpose layer, where 64 filters 3 by 3 kernel with strides equal to 1 is used. Next, leaky ReLU function applied to update the weights through backpropagation. Next, this value is passed through second convolutional transpose layer, where 64 filters 3 by 3 kernel and strides equal to 2 used. Next, leaky ReLU function applied. After this, it passed through the third convolutional layer, where 32 filters 3 by 3 kernel and strides equal to 2 used. Next, leaky ReLU applied. After this, it passed through fourth convolutional transpose layer, where one filter 3 by 3 kernel and strides equal to 1 used. Sigmoid activation function applied to this output for the normalizing its values between 0 and 1. Here, trainable parameters are 100 to 1017 and non-trainable parameters are nil. Up till now, we have designed the encoder and decoder. Now we will join these to form a full encoder, the full autoencoder. To train the encoder and decoder simultaneously, we need to define a model that will represent the flow of an image through the encoder and back out through the decoder. Luckily, Keras makes it extremely easy to do this. Using this code, the input to the autoencoder is the same as the input to the encoder. So we have used encoder input. Using this code, the output from the autoencoder is the output from the encoder passed through the decoder. So we have used encoder output using this code. Model designed with Keras model that defines the full autoencoder, a model that takes an image and passes it through the encoder and back out through the decoder to generate a reconstruction of the original image. Now that we have defined our model, we just need to compile it with a loss function and optimizer compilation. Using this code, Adam Optimizer is a stable optimizer. It used for update the weights in the neural network based on the gradient of the loss function. This code defines root mean squared error loss function for the brighter reconstructed images. The neural network using loss function to compare its predicted output to the actual output. It returns a single number for each observation. If number is greater, the network has performed version for this observation. Using this code, we have compiled our autoencoder model with Adam Optimizer, root mean squared loss function, and matrix parameter accuracy. We can now train the autoencoder by passing the input images as both the input and output. Training the autoencoder. Here we have passed input images as both the input and output for training the model. Number of images per batch is we have given 256. Shuffle is equal to true means the batch will be drawn randomly without replacement from the training data at each training step. Total 10 epochs for the full training image. From this result, approximately 220 microseconds for each observation taken. Loss has fallen from 0.0792 to 0.0445 and accuracy almost 80%. Reconstructing original image from code, that is the representation vector. Our goal is to reconstruct original images from code. For that, using this code, we are going to take 10 digits randomly from the test dataset for our autoencoder. These values are indexes of 10 digits which we are going to take as test images as input to encoder. This line showing for 10 numbers. This code gives a 10 randomly generated indexes of 10 digits test images. These 10 images put in a list using this code. Using this code, we are converting these 10 images into latent space points or 2D vector using encoder. These 10 latent space points are passing through decoder for reconstructing the 10 images. Now we will write code for plotting the images with matplotlib.pyplot. This is the final code. In its output, first row is our input test images, second row is 2D vector points, and third row is our reconstructed images. So far, we have designed a convolutional autoencoder and passed 10 input images of 10 digits to encoder and obtained its code, that is the representation vector. This vector passed to decoder. From that, we have obtained reconstructed images of 10 digits. So our job is over. Let's dive into deep. Latent space, that is representation vector. How can we plot the two-dimensional latent space in a scatter plot? To visualize latent space in 2D, we have to use matplotlib.pyplot library. Here 5000 input images are converting into representation vector, that is latent space. Using this code, 5000 input images of digits are randomly selected from a test dataset. Now using this line, all these numbers are taken into list for passing to encoder. Using this line, all these numbers are taken into list for labeling. Using this line, all the numbers are passed to encoder. Now we use the matplotlib code. Now see the output. This is the 2D latent space in color. Here every dot represents a 2D vector point of each digit. For example, 2.7, minus 0.6 for a point. Similarly, all the points also. The sidebar in color represents digits numbering. Analysis of the latent space. Can we do reconstruct image by selecting a point from latent space by using this convolutional autoencoder? Let's analyze our latent space. We can start to investigate how it is representing images in the latent space. There are a few interesting points to note. Point number 1. The plot is not symmetrical about the point 0, 0. For example, there are far more points with negative y-axis values than positive, and some points even extend to a y-axis value of less than minus 10. Here, all the points scattered unevenly. If you choose any point from the latent space, there is no guarantee that chosen point will be centered around 0, 0. This makes sampling from our latent space extremely problematic. Point number 2. Some digits are represented over a very small area and others over a much larger area. This explains the lack of diversity in the generated images. Ideally, we would like to obtain a roughly equal spread of digits when sampling random from our latent space. However, with an autoencoder, this is not guaranteed. For example, the area of 1s is far bigger than the area of 8. So when we pick points randomly in the space, we are more likely to sample something that decodes to look like a 1 than 8. Point number 3. There are large gaps between colors containing few points. It explains why some generated images are poorly formed. We can see 4 points in the latent space on their decoded images, none of which are particularly well formed. Remember, our goal is to be able to choose a random point in the latent space, pass this through the decoder, and obtain an image of a digit that looks real. If we do this multiple times, we would also ideally like to get a roughly equal mixture of different kinds of digit. That is, it should not always produce the same digit. This is also the aim of our autoencoder when choosing random points from latent space wall to generate new images. Let's testing our autoencoder by choosing random points. Using this code, we are passing 5000 digits of images to encoder. Our encoder has generated 5000 latent space points and 400 random points, which are in black dots, are chosen to reconstruct the digits images. By observing this output, if we want to choose points where the latent space points are not generated, this autoencoder has not decoded legible digits. One strange thing is, even the chosen points are right in the middle of the domain, also not decoded into well-formed images. This is because the autoencoder is not forced to ensure that the space is continuous. For example, the point 2, minus 2 might be decoded as image of 4, but there is no mechanism in the autoencoder for a point 2.1, minus 2.1 also produces a satisfactory 4. In two dimensions, this issue is difficult to describe. The autoencoder only has a small number of dimensions to work with, so naturally it has to squash digit groups together, resulting in the space between digit groups being relatively small. So the generated images from the latent space may not be satisfactory by this autoencoder. Variational autoencoders can solve these problems by introducing randomness into the model and constraining how points in the latent space are distributed. Variational autoencoders are a powerful tool in the generative modeling toolbox. We can transform our autoencoder into a variational autoencoder with a few minor adjustments, thus giving it the power to be a generative model. In the next tutorial, we will learn how to build a variational autoencoder using Keras. Bye bye friends, see you all again. Signing off, Kishore Kumar Vajja from iRobot.